which is the raccoon capital of the world, I believe. So Benedict is going to talk about mesh networking, IPFS, and other distributed ways of building your own internet. So yeah, please welcome Benedict.
Thank you. Thank you everyone for being here today. It's really exciting to see people interested in peer-to-peer systems. It's also a really good timing. I have been having a lot of thoughts about a talk like this, and this gives me a perfect opportunity to organize all this information together into a 1-hour presentation. So let's begin. Peer-to-peer protocols for our cyber commons. I'm going to start with talking about living with our internet. That could mean many things to different people. It could be very optimistic, all these great things happening on the internet, and now we're at a time where we can create many things that were not imaginable before. Or it could be like very negative. It could be like coping with the internet. Every day you're like, it's not the web that I'm used to before. That's also possible. And then the next step would be talking about networks that exist right now in the distributed web. And then we're going to start talking about protocol politics of our networks. What that means is some of the design decisions in these networks embed certain politics that allows for certain types of societies to emerge. And we want to explore the protocols in the context of that. And then lastly, fabric of our cyber commons. What is it that will make up the future internet that we all want? So let's start with living with our internet. That's pretty much the front page for the internet right now. A lot of times when I start clicking around, I click into a link, and I'm prompted with a Facebook login or like some other siloed data login. So Facebook has successfully inserted itself in the middle of solving this very hard problem, content distribution on the internet. On the internet, if you control the demand, you control a lot of the supply. And Facebook became this middleman that controls a lot of the demand because everyone is on the network, and content publishers start publishing not only to their own site, but also to Facebook. And if we look at statistics, we actually see that Facebook has grown a lot in being the referral source of traffic to many top web publishers. Google actually remained pretty stable. Like from 2012 to 2015, they occupied about the same percentage-wise. But what we see is like the other ones, referral traffic from random websites is really going down. And one day I was browsing and I discovered this news site being served from a Google domain, which is really weird to me. So then I started looking into it, and I found this thing called accelerated mobile pages. Basically, because mobile adoption is going up, and Google is taking content from the news sites. News sites are publishing in a way that AMP can ingest it, and then serving it through Google CDN instead. So in this like very mobile first world, Google is, again, it's good for performance reasons on our phone, but it also inserted Google into the middle of serving content. And this sort of mobile ecosystem is a little dangerous because it's even more restricted than our desktop environments. We have two ecosystems basically. And for example, in the Catalonia referendum, we had Google Play being asked to take out the referendum app, and that happened. And in the Apple Store, the takedown of apps are even more unreasonable. And when we talk about apps, ecosystems, we can take a look at our phone and how many of those apps maybe are not branded Google, but how many of those actually are indirectly owned by Google or Facebook or Apple or one of these major players on the internet. Which brings us to the question of data ownership under surveillance capitalism. Whether we like it or not, our web is currently incentivized in a way that encourages surveillance capitalism. It's not that anyone working at these companies have a particular interest in our personal lives, but the incentives are lined up in a way where data sells, where it's important to own a lot of the people's data in order to serve ads targeted to that group of users, which in turn is how to pay for all this development work. And we may think that we can just like put away our phone and we're not tracked. We can turn off our phone or like I have nothing to hide, but it doesn't stop here. In Toronto, we have a project called Sidewalk Toronto. It has two main players. One is Alphabet-owned, Sidewalk Labs. The other one being the government. It's a project where at the waterfront of Toronto, there will be a little neighborhood that's built from the internet up. This can be viewed favorably. Some people think it's really great to not have all these inefficiencies in our public infrastructure. Now we can use data to drive the next wave of innovative cities. So it means IoT, it means automation, but we're now into 2017, 2018 part of this, where we just had a round of public consultation, and there has been a lot of friction and a lot of frustration with the public consultation process. The data policy stuff is never addressed properly, and multiple people on the Sidewalk Toronto side have resigned over this from the advisory panel. So we're still in this uncertain phase whether this will continue or maybe it would never happen. Nobody knows. When we start having internet infrastructure permeating all of our living spaces, we have to think about social control with this level of data aggregation. It's not news that many platforms are struggling with moderation problems, censorship problems. It's a very hard problem to solve when you have one person having, or like one organization having control over all that data. Reddit with their quarantined subreddits, basically making certain subreddits harder to access and not serving ads on them because like some brands are like, these are like very unsavory subreddits. I don't want any brand association with them. And similar stories with YouTube. Some videos are not getting ad revenue. So we don't really have a solution to this. And then the next thing is digital imperialism by high barrier infrastructure. We have our net neutrality erosion in many places in the world now. US, that already happened. And in Canada, there's also conversations around prioritizing certain traffic. And when we think about who is in the best position to have higher priority, we have to think about who owns, who are the users of most of our traffic. It's the bigger providers of web content. And not only do I think that these companies will be favored in the future, but they're also building private infrastructures, building fibers that connect different cities. So you see how some of these fibers are owned by Microsoft, and you have this one that's connecting to South America that's owned by Google exclusively, and then you have some partnerships between Facebook and Facebook and Microsoft. So we have all these things that we used to have separated from the web providers. Now we are having them owned also by the providers of content on the internet. And then when we put another map on top, who currently has internet adoption, we see that there are regions of the world where in the next 5 years will be the first time that many people are finding out and interfacing with this world, which is deeply troubling. Because what is the internet that they're going to see? Are there other ways that we can build networks that do not have these tendencies? And this brings us to the next part of the talk, networks of a distributed web. And in this talk, I want to speak about a few networks that are existing and the protocols that they use, which in later sections we can talk about in relation to the previous problems that was in the previous section. So some of these networks are Ether. Ether is like it's like Reddit, but completely peer-to-peer. So it does have to tackle the moderation problem and all that sort of stuff, but in a decentralized way. Giphy.net is a telecommunication physical infrastructure covering most of Catalonia. It welcomes both businesses and individuals or community organizations, all bound by the phone compact. It's in existence for more than 10 years, but then networks that eventually made up Giphy has almost 20 years of history. And it's the primary internet provider for a lot of communities. Hyperborea is a CJDNS network. CJDNS is the protocol that forms an encrypted IPv6 network. And it's very permissionless, meaning anyone running some software can join. And Hyperborea right now has more than 1,000 nodes, and we're going to talk extensively about this. Interplanetary file system, also called IPFS, with its networking layer called libp2p. It's a content-addressed hypermedia protocol. What that means is you can fetch stuff from the network without addressing a particular host. We'll talk more in depth about that. Scuttlebutt, Secure Scuttlebutt, the scuttlers. It has the idea of mapping network topologies into social relationship topologies. We can see what type of communities emerges from that. The Yggdrasil network is closely related to the CJDNS network, and it takes a different path to how distributed routing works. And there are many other participants in the distributed web, but these are the ones that we'll focus on. So let's begin with Giphy, the network in Catalonia. The phone compact is more like a license or a contract than a protocol, but I think we can also look at it from a protocol perspective. It establishes shared values among community organizations and businesses. That's primary reason is to provide internet access to neighborhoods and people. The compact is there to facilitate and maintain the expansion of the network. And the physical infrastructure consists of wired, wireless, and fiber networks altogether. It's there to prevent privatization of physical infrastructure, but also at the same time allowing business incentives to exist so that it can be a maintained network. So the phone compact consists of four main points. You have the freedom to use the network for any purpose as long as you don't harm the operation of the network itself. The rights of the users or the principles of neutrality that allows contents and services to flow without deliberate interference. So this already, any organization that's bound by the phone compact already has these anti or net neutral principles in mind. These are like the shared values that I'm talking about. You have the right to understand the network and its components, and to share knowledge of its mechanisms and principles. So you can't exclude people from like proprietary knowledge. You have the right to offer services and content to the network on your own terms. You can't force other players to behave in certain ways, as long as you're like bound by this compact. You have the right to join the network and the obligation to extend this set of rights to anyone according to the same terms. This is like a copyleft type of rule. And now let's talk about the technical layer. It's a mix of different types of links, and usually it's run by proprietary carrier-grade hardware from Ubiquiti or MikroTik. Routing, there are these small regions inside the circles that use more dynamic routing mechanisms like BMX6 or OSPF. And the backbone network is another layer where each community, say like Barcelona and Mataró, they would like talk through more stable routing mechanisms with BGP. The network itself is maintained by ISPs that are bound by the phone compact, and also community organizations. So what does it actually look like? This is on the roof of a city that's 40 minutes away from Barcelona. This is one of the super nodes. Looking at this, you can see a whole bunch of Ubiquiti antennas. So a supernode is hard to visualize, but in this case, it's like the entire roof. It has more than 10 of these antennas pointing in all sorts of directions. And more recently, they built a fiber segment that's collaboratively funded by a user, which is a cooperative just down the street, and also one of the GIFI ISPs operating in the region, and the foundation itself. So collaboratively, they built a long segment of fiber that goes right up to this node, and they're gonna extend it from the co-op to this node very soon. So if you think about the way that people generally access the internet, you call one of the ISPs. But when the ISP says, "Oh, you live too far away, I'm not going to provide internet access to you," then you're kind of stuck. There's no way for regular citizens to participate in the building of the network itself. So that's very different when we have a commons infrastructure, where it gives opportunities to anyone to ask questions about, hey, why is it that I cannot build this segment? What if I pay for it? And because this segment that's built will eventually go back into the commons, so it will also benefit future users. So GIFI is really great. It allows for this type of interactions to exist, but there are also centralized components within GIFI. If you're a regular person trying to connect to that tower, you need to first get an IP address. This is done through a centralized database that you submit a form on the GIFI website, and the maintenance of the BGP backbone network is also quite centralized. So what are the problems with this type of centralization? If we look at the data of internet core routers, so these are not GIFI data. This is like internet BGP data, where we take forwarding tables and look at how many prefixes are announced. We see that the internet has grown in the last little while. It didn't become smaller. We had a lot more IPv6 prefixes being announced, and we can also look at the proportional distribution. Most of them are 24-bit announcements, meaning they are like small blocks of IPs that makes up almost 50% of the forwarding tables, which puts a huge load on these core routers, meaning we require more expensive specialized equipment and expertise to maintain. And all these small blocks of IPs actually make up only that tiny portion of the entire address space. So the next graph on the right is the same data, but shown as contributions to the address space. So if we want routing or connectivity to be more accessible to general people, not to a small group of specialists, we can think about routing and approach it differently. There's a topic called compact routing, which in relation to BGP type of interdomain routing, it focuses on keeping small amounts of routing data at each table, rather than piling all this work onto a core network infrastructure itself. So it also makes it very difficult to do, because now what we used to do is have a full view of the network. But without that, how do we determine shortest path between 2 points when I do not see the entire network? Because algorithms like Dijkstra, as used in OSPF, assumes like a full view of the network and use that data to derive shortest path routing. So the goal is to not find the shortest path all the time, but have a bound to how much worse the path would be. So instead of maybe 2 hops is the shortest path, a stretch of 4 would mean a stretch of 2 would mean like you now have 4 hops as the upper bound, and try to also, in most cases, be able to route the shortest path. And at the same time, allow for routing tables to not grow at the same rate as the number of nodes scale. And you can also classify compact routing into 2 different categories. One is name-independent routing. The other one is name-dependent routing. Name-dependent routing means the maintainer of the network can assign names to the nodes, which means you can arrange them in blocks or like encode some sort of routing information in the names of the nodes themselves before deploying this network. But name-independent schemes assume randomly generated, completely fragmented address spaces. A harder problem, but it allows for networks to exist without like a layer of management on top. People can just join this network. So I want to steer our attention to routing traffic in a non-hierarchical network with flat IDs that are all self-addressing. And one of the projects is called CJDNS. It auto-configures an overlay network. It's actually very easy to join the Hyperborea network. And in this world, because anyone can join, all the traffic has to be end-to-end encrypted, and it uses the following crypto primitives. It self-assigns a IPv6 address by deriving one from the cryptographic keys. This is a private block of the v6 space, and it does source routing with a Kademlia-like distributed hash table, which there are 3 things here that are special terms: self-assignment and source route and distributed hash table, which we're going to go into right now. Self-assignment of IPv6 addresses, how does it work? Basically, you do 2 rounds of SHA on the public key, and then you truncate it into a IPv6 address, a valid IPv6 address in a particular space. So we'll never get a conclusion because there's so many addresses. But what about the birthday problem? Is it possible that we'll derive 2 IPv6 addresses, or like 2 public keys, 2 curved keys, and they end up with the same IPv6 address? So this is the calculation for how likely that could happen. And Basically, it's very unlikely that that might happen. Next, we can talk about Kademlia DHT routing. We have a node called 0011. This represents an IPv6 address in simpler terms. That's the black dot over there. Kademlia allows us to learn paths from every neighborhood. So this node has a path which is different from peering. A path means it knows the hops to get to one of these neighborhoods. So each node would keep a routing table at each XOR distance bucket. And this allows us to know our local neighborhood well, and at the same time have less knowledge about distance ones, but also have a way of reaching each neighborhood. So one example is when I try to come to Oslo, I wouldn't ask someone in Toronto how to go to NUUG. I would ask people how to get to Norway, and then how to get to Oslo, and then I would ask someone how to get to NUUG. So there's like neighborhoods that maintain more local knowledge. Let's go through an example of searching in this world. 0011 would first is trying to search for 1110. 1110 is over here, 1110. But it doesn't know how to get there. It's gonna ask 101. That's the arrow that's labeled 1, because it knows how to get to 101. So from 101, it learns about 1101. And then successively, it would query like this. And then iteratively, you get to closer and closer to your destination. And what closer means in a space that's not physical, that's not geographic, Kademlia uses something called an XOR distance. This is a XOR between the two addresses. So 1101 is the XOR distance between these two nodes. It has this unique property where between two nodes, it has a distance that no other two nodes. Like you're at a certain distance from this node, but some other node, you're at a different distance. And the distance between you and that node and that node and you is the same, because the XOR you can like do the opposite way, and it's also the same distance. So after 0011 learns a new path, it would put this path into its 4-bit position bucket. So now it knows the new path. And these buckets are of a certain size that you can adjust. And because you would know your immediate neighbor well, it means like your first, second bits are the ones that you'll end up filling. When you fill it up, you already know the entire neighborhood. Whereas every next hop, you're like, you have less knowledge about them. Because the space corresponding to your most significant bit is the space that hosts half of the network. Now, we can search. How can we actually deliver a packet from one point to the other? So we're going to label these two nodes. In the previous example, Rick and Morty. And we start like this in CGDNS, and source routing part of CGDNS. You assemble a set of directors that you tag onto a packet. So every packet gets this 64-bit thing tagged onto them. And you see here multiple directors. They're like instructions to turn left or right. And so because Rick knows the path to Morty, it would put together these directors, expecting that its next hop and its like second hop, third hop would read. When Morty gets this thing, it would pop its director and just send it down its write interface. Write interface could be, it means you have an actual cable connected to the other node. Of course, this cable can be wireless or it can be like tunnel over the internet. It doesn't really matter what this idea of a cable is. but it will send it down that interface. It could be like your if0 on your machine. So it does that, and the packet reaches Summer. Summer is a peer of Morty on that interface. And then Summer now sees the down director on her interface. So it would do the same thing, and then iteratively, the packet will eventually reach Morty. Oh no, sorry, not reaching Morty. This is reaching 1110. And then you may see that on the left-hand side, there's a director that looks weird because by popping it, you append it to the end, and then you can flip it to get a return path. OK. So Hyperborea now has more than 1,000 nodes, but it has some limitations at this scale. First of all, the XOR address space has no resemblance to physical space, which means I can be sending a packet from Toronto to Oslo and then back to Vancouver and then to Hong Kong. So some of the routing is very inefficient in the real world. In network space, it makes perfect sense, but in a physical sense, it incurs a lot of unneeded bouncing around of packets. And a bigger problem that we're running into is in a wireless mesh network. Nodes don't know the quality of links. It's OK when you have stable links, but when you have wireless droppy and changing topologies, source routing doesn't give you visibility deep into multiple hops, and that causes connectivity problems. And another problem is once the network is big enough, we start getting many hops, and the 64-bit packet header cannot fit all of them. So CJDN has started implementing the idea of a supernode, which means some nodes can hold the whole routing table, and it starts offering this as a service to a path discovery as a service to the subnodes. So it can run Dijkstra to find shortest paths, but the downside is a point of centralization, even though the traffic themselves is still routed through the mesh. Question?
I think it was on 2 or 3 slides ago, we saw that as part of routing or as part of path discovery, you were querying a node would query other nodes.
Yes.
Does that introduce the vulnerability in if a node or you populate a bunch of intentionally toxic nodes?
Yes. That's a very good question. And this is a problem that source routing can better address in comparison to greedy routing. The question was, is it possible for nodes that are malicious to compromise the network by inserting many nodes that route traffic in a bad way? So in source routing, it means the source node actually has some level of control over how the packet traverses the network. I can go down a path, and then it never reaches my destination. So I can change the directors to go for another path. So at least I can reach the other end through this routing around bad nodes process. And then over the longer term, the malicious nodes will get unpeered because they're whose first hop peered to it is getting no benefit from this node. So there can be some kind of blacklisting mechanism. Does that answer the question?
Yes and no. I mean, it still seems like there's potential for if the intention isn't to target a specific node or a specific type of traffic.
Right.
I'm sure there's some threshold over which the number of negative nodes would just start impacting and fragmenting the network as a whole.
Right.
So misleading. I guess because it's encrypted and so on, you can determine if you've reached the right destination, and yes, you could do some pruning based on not reaching it in sufficient time. But if you are, for example, sending back incorrect routing data as to your local neighborhood, somebody in Oslo is telling somebody else going to Oslo not where they are, but where their neighbors are, or telling them the wrong things there, then that would screw everything up.
yeah, if you start like telling people paths that are bad, then those paths will have to be get pruned from the routing tables, and then the network has to have some way of dealing with you, like this player that's announcing the bad paths, obviously this gets into a question of what percentage of nodes can be can do what type of damage to a network, and also what is the cost of generating many nodes in a network. There's another question.
Yeah, somebody just started music in the next room. So, so I actually have two questions.
Yeah.
One is so this, from my understanding, this is a full graph, so it's not a tree, but the address assignment is based on the cryptographic hashes. So, what's the definition of neighborhood? It seems like you can end up wherever in the world and just get your neighbor randomly.
Yeah. So a neighborhood is a network neighbor. It is determined by your XOR distance. So if we take our IPv6 addresses and XOR them, and the first difference bit is like the most significant bit, then we're in very distant neighborhoods. You are in the other half of the network that corresponds to my most significant bit bucket. So I will only keep maybe 10 nodes in each routing table, in each bucket that corresponds to each of the bits. So I will only know 10 nodes from that entire half network space. Whereas if you're right next to me, like our IPv6 address only differ by the last bit, then I would have 10 slots to hold all that. So your node would always be in my routing table.
Yeah, but you could be anywhere in the world, even if the yeah.
Exactly.
Yeah.
That's why that's the point about XOR space having no resemblance to physical space. So neighborhood is not like real world neighborhoods.
So that okay, because then how you introduce like how do you do your bootstrap? How do you introduce yourself to the network at all? And secondly, what's the mean and max query? The number of queries you need to do to get to a node, mean and max.
I do not know the answer to like the min and max question, but how do you enter the network in the first place? You need a peer. You have to peer to any node that's connected to the network. And CJDNS does it through local peering. So if I run a laptop here and then you have a laptop that's running CJDNS, we will peer because we're on the same Wi-Fi network, or we have a cable to each other. But you can also tunnel over the internet to peer, and that requires like coding other person's peering information into like manually. Okay. Which brings us to so all these routing problems for specific use cases bring us to the next part, the Yggdrasil network, named after the mythical world tree, shares the same addressing scheme with CJDNS, similar. It also does a end-to-end encrypted network, but it routes traffic completely differently. That has resemblance to physical topologies of the network. So now this is the geographic neighborhood thing. In this way, it allows all the nodes to make some assumptions about the network, but without holding the full view of this routing tree. It guarantees that there's a way to route to each node, and because it's a spanning tree, it would be, I think it would scale to log n. And it's a very new project, but so far, nodes usually get the shortest paths. So Yggdrasil does a spanning tree at the switch layer. And it elects a global root to act as the 0,0, like as the origin of that tree, the tree roots. It still uses a distributed hash table to look up coordinates given the IP address, because like if I know a IP address and I have no idea where it is, I can still use DHT to query it in order to learn the coordinates. The edges of the tree are always direct peers, and it's ranked because you might have like 10 peers, but the edges are based on stability of that link. So this immediately adds some knowledge of local, like physical space into our routing. And coordinates are shared with peers and cryptographically verifiable from the tree root. And the switch layer uses greedy routing instead of source routing. We'll talk a bit about that. Each node keeps a partial view of the tree only. And this is the scaling is order of p times log n, p meaning the number of peering relationships in the network. There are two ways to route. The worst one being, well, there are not two ways to route. There's an upper bound to routing. The upper bound to routing is walking the tree. But most of the time, because we're using greedy routing, which means I pass a packet to you, assuming that it would go walk the tree, but then you having knowledge to more than what the tree knows, you can just pass it down a different path. That's like a shortcut. So let's do an example of this. It's a lot of information. There's a node here that's green. The yellow nodes are the ones that it has a cable connecting, basically. And now we're trying to route from this to D40C. Its global coordinate would be 352, which is like this node right here. So if you go down the tree path, it's going to go this node, and then that node. But the greedy path is, hey, I'm already up here. I'm just going to send the packet right to this. And it's possible that a node doesn't actually know the tree roots. But from some information based on its coordinate, it can infer some topology of the tree. And then it'll only learn about the tree root when it actually needs to use it. It'll send something, maybe if you would need to send something to that node, and then you'll go through the DHT and query its IP, and then, oh, you're actually a tree root. Yeah. Any questions about this so far? No? Okay. And, so we have an ad. Because we want a full internet experience. So in putting together these slides, I was talking with different people that are designers of these protocols. And because Yggdrasil is a very new project, Neil, who is one of the contributors to this, he was saying, hey, we actually need a lot of people to start scale testing this network, because in theory, it will scale very well. So this is the matrix channel and IRC. If anyone was interested, join and ask for Neil, Auxilia. Okay, so do we want to take a break, or shall I continue? Just keep going. Let's do it. Okay, we're done with routing IP traffic. We're going to move on to application layers. Interplanetary file system is a protocol that allows us to store distributed content on the IPFS network. It provides stable content addresses and to locate them, and also verify integrity of those contents. It can do concurrent downloads. Say you're fetching a big video, you can fetch the chunks from everyone, so kind of like BitTorrent in that sense. And it would auto scale the network with the network capacity with content popularity, because like you start fetching it, you start seeding it to others. The lib2p2p is the networking layer that traverses NATs and does announcements like node discovery. It used to be part of IPFS, but now it's like its own project, because like more other projects can actually benefit from something like lib2p2p. So let's talk about content addressing. It's the idea of referencing content by hash. In traditional internet traffic, we address by host. We go to youtube.com or we go to reddit.com, and then they have the local addressing scheme. So when someone gives you content, you're trusting that they're giving you authentic content. But there's another way to address content based on hash. I can say, I want this. And then you don't care where it comes from. It can be from an untrusted source, because once you get the file, you can hash it, and then it gives you this hash. So that brings the question of what hashing algorithm is used to produce this hash. In IPFS systems, there are multi-star protocols like multi-hash, which are self-identifying protocols, self-identifying formats. So basically, in this case, the 1.1 tells you it's a SHA-256, and then the 2.0 is the length of the digest. And then what follows is the hash. So the whole thing is the hash here. It's the address, I mean. And there are like multi-hash, multi-header, all kinds of multi-star formats. What multi-address allows you to do is layer different protocols on top of one another. So you can see a HTTP over TCP over IP6 in the first example. And then you can start layering things on top of the Tor network that runs the Onion protocol. So you can bridge content across different networks like this. So what does it actually look like downloading content from the IPFS network? First, you ask a peer. And this is how you get to the peer. You're talking IPFS protocol to a node ID over TCP, over port 4001, over IP6, that IP address. And I want to locate the content that actually, the content is actually located at this red address here. And you find it, you can download it through this other path. Once you have the content, you don't know this node that gave you the content, but you can do a SHA, and then based on the address, you know that it's a SHA-256, and you verify that it is the content that you want. And you also cache the content to help scale up the capacity of the network itself. So that's content addressing and multi-formats in IPFS. We can move on to another network called the Ether. This is a very, V2 of Ether is a very new project. It's now in closed alpha, or it should be released like within a month or so. It's like Reddit, but peer-to-peer. It has to solve these problems of maintaining participant identities without a central authority. Instead of having persistent content like IPFS, it optimizes for ephemeral content and metadata as well with spam deterring mechanisms. It facilitates community content moderation. So it has a layer protocol that's like specifically for moderations. It ensures that participants' actions are not trackable by the servers, which also run on your same computer most of the time. But then the UI layer doesn't actually know, doesn't actually expose any information of what the users are viewing. And fast and scalable synchronization across the network. So we have to talk about the idea of the Sugos triangle. You can get humanly memorable names and secure names and globally unique identities without some sort of central authority. You pick two. So in the Ether system, it uses a pet name system where the identity is a cryptographic key, so it's globally unique. And everyone can self-select a memorable nickname and try to convince others to take it. But sometimes you have collisions, like we both choose the same name. I would choose Ben as my Ether name, but that's a very common name, so there can be multiple Bens. So the viewer can actually resolve these by having their own names to associate with the keys in a pet name system. You can say Ben from Toronto or like Ben from Oslo. They're two different identities, but even though they're advertising the same name. The way that Ether deals with this is to have naming authorities that you can subscribe to, and you can rank them to resolve the user decision being the top priority. Many of the design decisions in Ether is like user priority overrides everything. Same with content moderation. To avoid spam across the network, there's a proof of work mechanism that any action you take, even liking a post, requires you to like do some computational work. So kind of like Bitcoin type of proof of work, except you're like not actually mining anything. You're just you're just proving that I'm putting work into this. And then all the nodes that are syncing this information would verify the cryptographic proofs. Yeah, so with censorship and moderation is opt-in. Participant can say, can opt into certain filters or moderators, but then you can vote out people, or you can just like take them off your moderator list, and then all their moderation would not take effect to your browsing experience anymore. Ethereal data syncs. Applications run both a front end and a back end. They're both running under the same application, so you don't really have to differentiate them, except in like constrained devices where my phone may not want to run a back end. This separation is very good because it allows me to run the back end on Raspberry Pi and my phone not having to run that at home. And because because data is like all pushed to the phone from the back end, like not the full data, but like counted data. Like if there are cryptographic proofs to all the likes of a post, it doesn't have to send you the counts. Like each it can be a reduced data format, but the client still does the verification of the proofs on the front end. This way, the back end doesn't know what the user is browsing because it always sends everything. So after Ether, we can talk about the Scuttleverse, which is the list of projects built on top of Secure Scuttlebutt. In this case, I'm showing a snapshot of Patchwork, which is a social media, it's a social network that the network data topology is resembling of the friendships and social links of the people that are participating in this. It optimizes for off-grid use, does not assume constant internet connectivity, prioritize subjective decisions. Data visibilities are local because the data are hosted like among your friends. It maps the data topology to the network, to the social topology. And it facilitates discovery modes, like meeting people in a virtual pub that mirror social interactions. So each person keeps a append-only database of signed messages. It uses pet name systems for identities, and each participant signs and appends to this personal log. A friendship means a public key exchange. So we each pin each other's public key, and we cache each other's data. Messages are all signed for public and encrypted for private. It allows us to control our own social bubble rather than having this algorithm that thinks this is content that I like and prioritizes those in my friendship feed. I have active control over this. I can like start unfriending a whole bunch of friends and I no longer cache their data, and then I just start not seeing all those content. They're like not on my databases anywhere. So we can go for an example of this. In this case, we have Summer and Morty as friends. So each of them keeps a signed log. Morty is keeping a copy of Summer's, and Summer keeps a copy of Morty's. Whereas in this other place, there's Unity, who is not a friend to that network, has no social link to that network. No one even knows Unity exists on the other side. So there's no global search. Like you can type in an email address on Facebook and it searches the person. And there's no huge Facebook database to be profited off of, and also as an attack target to people who wanna steal that data for whatever purpose. So what happens to that graph when Rick joins the Scuttleverse? Rick is gonna come in. Rick knows Morty and Unity. So Rick is gonna clone Morty's database, and Morty is going to do the same thing, and then Unity is going to keep a copy of Rick's. So now all of a sudden, the worlds are connected. And you can adjust how many layers of caching you do. So in this case, Rick can actually start caching friends of friends, for example, and then it'll see deeper into the network if it wants to. I know this is a really confused graphic, but it's only showing like first level cachings. So when you start caching deeper, you can, for example, I can go online, sync data to one of my friends, and then I go offline, but my mutual friend can go and go online after while I'm offline, and they can sync that data from another node in the network. Okay, so we're done looking at these 6 projects in the distributed network space. We can move on to talking about the politics that are embedded within these protocols. How are we on time? We're 1 hour, right? Okay. So this is a part that's inspired by a reading called "Do Artifacts Have Politics?" In infrastructure, do they lead to certain societies? Or do they favor certain societies, certain modes of controlling that infrastructure, and in turn controls the behavior of people? So the question here is, do protocols also have politics? Let's take some example topics. Traffic routing on distributed non-hierarchical networks. So this is a quote from Auxilia. For a large network to scale, it must be subnetted into smaller ones to more easily manage them, which then must in turn be networked together to form a network of networks from inter-network connections, such as the internet and BGP and our ISPs. This requires some level of expertise and planning to do, and tends to favor hierarchies wherein small networks are largely at the mercy of larger networks. The only connection your LAN has to another network is your connection to an ISP. And peering or directly connecting to your neighbor's LAN to fetch information is very, very uncommon. So we can draw a ISP link like this. And if we start having self-addressing networks, we can have a mesh like this. We still need to go through some ISP, but at least this diversifies our choices. And having these protocols that are not storing the entire BGP table, it allows us to start using available hardware, cost accessible, and open hardware like the Libre router and Raspberry Pis. Another topic we can discuss is name assignments. Here's a quote from Ansuz, which builds a DNS system based on SSB. If ICANN is a monopoly, if ICANN's monopoly is a kind of feudalism, then Namecoin's method of